All right, so continuing our discussion on chapter 5, remember terminal velocity occurs when the upward force is equal to the weight of that object. Thus, as this flying squirrel over here, he's going to fall at constant velocity but not accelerating. So that's what it means to be at terminal velocity, when that upward force of the air equals the weight downward. Terminal velocities depend on how massive the object is and also how it's falling, the shape of it. When you dive, you can manipulate your shape by whatever way you orient yourself as you're falling into the water. Um, Even objects really massive and dense like baseballs are going to reach terminal velocity if you drop them from high enough points. Now we're going to kind of move directions here. In terms of applying force, there's different ways to apply force that make a huge difference. And if you look at the pictures on the side here, think about if someone wearing high heels were to stand on your hand, I'm sure that would hurt a lot worse than someone the same weight wearing Converse sneakers standing on your hands. And the reason that has to do with pressure. Uh, just like if you're holding a book, if you hold it with the cover down, it's going to feel different than if you hold it edgewise with the cover to the side. But no matter what way you put that on the scale, it's going to read the same amount. And the reason it feels different is because of pressure. Pressure tells us how much force is exerted over a particular area of space. So the pressure is the amount of force per area. We find the pressure by taking the force and dividing it by the area over which it's applied. Notice if I have a large area over which that force is applied, it's not going to be that much pressure. But if I have a really tiny area, as in the case of a high heel or even a knife, a very small area, I can apply less force with a sharp knife and put the same pressure on my food as if I were to apply that force with a dull knife. The unit of pressure is Pascal, named after the scientist Blaise Pascal. So this is why when you lay on a bed of nails, it doesn't do much, because that force is applied over a great area, thus reducing the pressure that you feel. If you took one nail and sat on it or laid on it, it would do a lot of harm to your skin, because all that force that you're putting down on the nail is applied over a very small area at the tip of that nail. Again, switching gears here, now we want to use what we've learned about Newton's second law and discuss that in terms of free fall. Now, we have this comic here. If I drop the bag of clothespins and just a single clothespin at the same time, we want to know which is going to fall to the ground first. Now, I'm sure you remember they should hit the ground at the same time, but let's say you didn't know that. Pretend you're reasoning through this like the two characters at the bottom of the screen. So the character wearing red says, that's easy. The bag of clothespins is heavier, which means the gravity pulls on it with more force. So the bag of pins will accelerate more because it's being pulled more. It's going to hit the ground first. But the other boy wearing purple says, not true. The bag of clothespins has more mass, which means it has more inertia. It's going to be harder to move, less responsive to gravity, and it's going to lag behind the single pin. So who is right? Well, we drop them. They both fall at the same time. Why? Well, if we look at it, the bag has both a greater weight and a greater mass. It offsets the fact that the pin has a smaller weight, but it also has a smaller mass. Remember that acceleration is the force divided by the mass. So that force or that weight, if it's bigger, the mass is also bigger. So you're taking a bigger number and dividing it by a bigger number, whereas with the pin, you're taking a small number, but you're only dividing it by a small number. That's why all accelerations are equal to g. So let's just look at this using actual numbers. Compare the acceleration of a 1 kilogram stone to a 10 kilogram cannonball. Now, we have here the stone and the cannonball. The stone has a mass of 1 kilogram. The cannonball has a mass of 10 kilograms. This means the weight, or the force due to gravity, the weight is going to be 1 times 9.8, which is not, well, let's just round up to 10 here. 1 times 10, which is saying it weighs 10 newtons. How much does a cannonball weigh? Well, the weight is going to equal 10 times 10, or 100 newtons. Recall that acceleration is equal to the force divided by the mass. So the weight, 10 newtons, divided by the mass, 1 kilogram, equals 10 meters per second squared. The weight here, 100 newtons, divided by the mass, which is 10 kilograms, gives us, lo and behold, 10 meters per second squared. Both of them giving us a result of g. Thus, the stone will accelerate at the same rate as the cannonball. So that concludes our discussion of Chapter 5. We've gone over Newton's second law, looking at how force and mass affect this acceleration, and then applying that to concepts such as pressure and free fall.